Hello and welcome. Today we're going to talk about applications of complex variables to some things that are more real in the real world. When we're going to talk about signal processing and a special tool called the Bode Plot. So this is definitely outside of the textbook we're going to use, but this is stuff that, because we're largely dealing with scientists and engineers here, you students will probably really enjoy learning some of these applications and how these tools of complex variables are incredibly important for they have a lot of descriptive power for things that are very important. So today we're going to talk a lot about circuits. And the idea of what we're going to do is applying a voltage, which I'll call VI, and that will be for input. And this is a function of time. And that's going to be we're going to think of this as a signal. All right, so the idea here is then we have a circuit. For instance, I'm going to draw out a particular circuit. So I'm going to apply a VI of t. And I usually write this as a little circle like that. And there's a plus and a minus. And it's connected by a wire like that. And there's certain circuit elements, and that contains capacitors, resistors, and even inductors. And for instance, here we'll put a capacitor, which we'll draw like that, and it has a capacitance C, and it goes like that. And then I'll also draw a resistor. This is going to be our first example circuit, and I want to measure a voltage, a V out, and that will be output there, and that also will be a function of time. And the big question then is, how does the circuit modify or augment the input. So that's the big question we want to answer, and so we need to develop some tools in order to do so. And many of you that have taken a signal processing class, this will be very familiar. And also, while we're doing everything with circuits here, we could also think of doing the same thing for a mechanical system using masses and springs and dashpots. They all have the similar properties and lead to similar differential equations. So let's write down the differential equations for this. I'll be a little bit we'll be a little bit cavalier about this. I'll assume that you all know how to do these sort of things, and I'm not going to go into a really detailed analysis of how to write down these equations, but rather we'll just use the result. So what I'll do is I'll write down the equation. We have our capacitance, which is a dV out dt plus 1 over R V out, and that's going to be equal to our V in. But in addition, in order to keep things a little crisp here, I'll multiply my V in by the same resistance VR, 1 over VR. And so I can rewrite this as RC dV out dt plus V out is equal to VI. All right, so there's a differential equation. And again, what we're interested in is that we want to find V out of t given an input. So this input could be anything. And in our previous ODEs classes, oftentimes we'd use some sort of input like a sine wave with a certain amplitude maybe. We'll just leave it at 1 there. And some a forcing frequency. So that would be a forcing frequency. Okay. In general, we could do that, but it turns out we can go. In particular, we could use a sine wave or a cosine wave, but it could be anything. And we'd really like to study the properties of this circuit to any signal. All right, so see if we can develop some tools that will do that. And of course, you probably are familiar with the Laplace transform. oops, the Laplace transform. So we can do a Laplace transform. And so we're going to assume, of course, that the V out of t for t less than or equal to 0 is just equal to 0. And any of its derivatives are also equal to 0. We want to start, we don't have to deal with initial conditions. We really want to know what happens to V over the long time from an input. So let's, and we don't want to think about any kind of initial condition that might foul up so we can, when we do that, we can also define this, RC, is actually, we can define this as what we'll call the time constant of the system, which is related to the capacitance in the resistor. And we can also define it as 1 over what we'll call this, this time scale can be thought of as a rate constant as well, omega naught. Okay, and that represents sort of an optimal rate for this system. Okay, so we can call this like a characteristic constant. All right, and then of course we take the Laplace transform of this system. So RC V prime plus V is equal to Laplace transform to the other side VI. Okay, so this is pretty straightforward to do. That becomes RC times S, our Laplace transform variable. And now I'm going to, and so these are V outs, I'm sorry. And we're going to rewrite this as V out tilde, which represents the Laplace transform, plus V out tilde equals what I'll call V in tilde. And I like the tilde symbol because it represents the idea that these are in the frequency domain now, so we think of them as oscillations. Okay, and we can rewrite this a little bit further and say that V out tilde now is going to be a function 1 over tau c S plus 1 times V out, or sorry, V in tilde. Another way to write this is of course 1 over 1 plus S all over omega naught times V in tilde. All right, so this is a really nice way to express the input-output relationship. All the complicated differential equation stuff becomes a multiplication. So now I'm going to get a new sheet of paper out here. I'm going to rewrite that. So we have the result of our circuit is our V out now is going to be related to 1 over 1 plus S over omega naught times V in tilde. All right. I'm going to label this now. This is what we're going to call our transfer function. Okay, so I put a dash there. Transfer function. All right. And clearly, this is a function of S, our Laplace variable. And what we can see here is the idea that this transfer function, if it's large, say, and this in general could be a complex number if we think of S as being a complex value, and we'll get to that in a second, but somehow it augments the input, the Laplace transformed input, to create an output. So whatever input you put in, this augments it through multiplication, and then you get to our output. All right, so we want to see what exactly this means. So in order to, we have to sort of kind of revisit some theory. Oh, oops. On Laplace transforms. And Fourier transforms. Okay, so let's do that. What we're going to do here is then think about this as let's examine what the Laplace transform of a function is, of course, we write it down as its integral from 0 to infinity of f of x. And maybe we'll actually put it in terms of time. F of t now, e to the negative s t dt. All right, so now let's make a restriction. Let's restrict. We'll say that we always say that f is really it's really a function for only on t greater than or equal to 0, right? We don't ever integrate over the negatives. But now let's sort of extend f to all of the real line by saying that f of t is equal to 0 for t less than 0. Okay, so now what we do is we have some signal, that's f of t, and it starts at 0, right? And goes off there. But now we'll just say that f is 0 for all the negative values of t. All right. In which case, I can then write my Laplace transform as this, right? Without loss of anything. We're just making an expansion then of what we're defining our Laplace transform. It does no harm at all because we've already restricted to functions that only have 0 for their negative part. All right, and then what we're going to do is also say that s now can be a complex number. Okay? So before we've always thought of s as being a real number, but if we let s be a complex number, and let's say let, in particular, s be I times omega, where omega now is another real value, but now we've taken s to be a purely imaginary number. And then, of course, we find out that if our Laplace transform of f, if I make it I omega is equal to integral from negative infinity to infinity of f of t e to the negative I omega t dt, this looks exactly like a Fourier transform. So now we see, provided our functions that we're interested in are 0 on the negative real t-axis, then we see that there's this really nice matchup between Fourier transforms and Laplace transforms. Okay, so why are we going here? Why are we heading down the path of Fourier transforms? The question is then, the idea here is that we actually have a really important result, and the result it comes from remember where you think of these things as an inner product. So an inner product on the domain R, then, recall from 3150 we had this thing called an inner product. If I had an F and a G, I can make it so for T on R. So we can write this as follows: dt. We can write such an inner product like that. Now, to extend to the complex plane, if we want to take functions now that are complex valued, all we have to do is define our inner product to be this. We just have to take our complex valued function and put a complex conjugate on there. So that's just a little tweak on what we know about our inner products. And now, of course, if we take g of t to be e to the negative I omega t, then clearly our Fourier transform now is simply that. Okay, so we can see that these inner products, or these Fourier transforms, are essentially an they're a projection on the family of functions g of t, like that, where there's a omega parameter in there. Okay, so the question then is, where are we headed with this? So I'm gonna state a really important result, And it's this notion that's going to help us. Again, what is our big question? Our question was basically we want to assess how inputs Vi affect VO. And what's really important is this notion of magnitude. How big is VI? And then how big is VO? All right, so what do we mean by that? If this is a question, what do we mean by bigness? Well, we have to have some notion of magnitude of functions. Okay, so this isn't an easy thing to answer, but we have a measure of that, and we're going to actually use that measure. So a magnitude of a function can be defined as this. We can actually define something. So where this could be a complex valued function, but we'll take it has only real inputs. The square root of the inner product of the function with itself, which we can write as f of t. And without loss of generality, we'll just put that complex conjugate there and say that this, of course, then looks like, if I was going to write this in terms of the complex magnitude, I would write where this represents that complex modulus. So now we have a measurement now of magnitude of our input. I can think of it as a squared input. It's just VI. Okay. All right, so this is looking good. So now we have some sort of measure of input. But now we have a really important result. We find that the important result, and this actually it's a theorem. It's called Plantarelle's theorem. And we're not going to prove this theorem or anything. But there's only one real asterisk to it. It has to be that the functions we're talking about have to be not just square integrable here like this, but also have to be to the first power integrable, have to be less than infinity. Provided we have this, and we also have that this is a meaningful statement, we can integrate this function. With that one proviso, we have the following statement we can make, that the magnitude of the function f is equal to the magnitude of its Fourier transform. So f of t is equal to its. So that means that if I want to talk about the bigness, if I want to talk about how big, well, I can take its Fourier transform, and whatever value I get here is the same one I get here. So by measuring the magnitude of a function, in this case, taking where we have this now is going to be, and I could put squares on these to make it simple, a little bit more simple to write down, which is going to be f omega times f bar omega d omega. This is now a way I can study, and this, of course, is the complex modulus here. Is a way of studying by looking at the complex modulus of our Fourier transforms. Now we can get information about how big the original function is. So now let's take this back. So with this result now, this notion of how big then transfers over to the Fourier transform space. So how big now can be answered either in frequency domain or in the time domain. Either one is fine. Okay, so now let's go back to our problem we had of our RC circuit. Okay, our RC circuit, we have the following result. V out S is equal to 1 over 1 plus S all over omega naught, where omega naught was equal to 1 over RC. Okay? And that was some parameter that we can, by changing the resistance and the capacitance of our circuit, we could get different omega values there. And that was our transfer function, which we call TS. And this is our input, S. All right, so now what we're going to do then is, of course, do exactly what we said, is if I take S equal to I omega, now we've changed variables here. We've now allowed S to be a complex number, in this case a pure imaginary number. We can write that down as follows. Oh. So omega over omega naught times VI I omega. And now what I'm going to do is take again, the complex modulus of both sides. And then what I want to do is, I want to assess the amplitude of, or the sort of the amplitude or the magnitude of V out with respect to V in. So of course this becomes like that. I can write it like this, but what I'm going to do then is, of course, I really want to know the amplitude or sort of like the amplification. So I should actually say this is amplification. Okay, so what I'm going to do then is divide both sides by the magnitude VI. In which case we get V out, the ratio of V out, the magnitude of V out over V in is equal to the magnitude of the transfer function. And now we know from before that if I were to average over all values of omega, I would get some nice measurement between the typical amplitude of these two functions. So we have some way of basically saying how this affects the real value or in the time domain by looking in the frequency domain. So let's now study this object right here and see what we can get from it. Okay. So as before, we have T I omega is equal to 1 over 1 plus I omega over omega naught, where omega naught was equal to 1 over RC. Okay, so I want to know what the magnitude of this is. And so the first thing we need to do is maybe turn this into a complex number that we can assess. So we see we have that imaginary part in the bottom, but we're going to do a little complex arithmetic to it. So I'm going to go over here. And now I'm going to do what we normally do by, we'll multiply by its complex conjugate, top and bottom. And we get 1 minus I omega over omega naught all over 1 plus omega over omega naught quantity squared. Okay, so after we multiply through all those things, so I haven't changed anything here. And now to get the magnitude of this thing, I merely take the squared components of each real and imaginary part. And first of all, we can take this out. The denominator is real valued, so we can take that out. And then look at this part right here. It's going to be the square root of the squared component. So it would be 1 plus, now we don't need to worry about the negative sign there, because that will, we just look at those parts, squared. There we clearly see that then this equals, after we see that this is actually that's to the first power, and this is to the 1/2 power. So together that makes 1 plus omega over omega naught quantity squared. All right, so we see now we have this represents essentially an amplification factor. Okay, and it essentially says for whatever frequency we're assessing then, so again we have this. This now, these things are equal here. This tells us the amplification factor at various frequencies, omega, between input and output. Okay, so let's now, so this represents a really nice way of talking about how much the bigness of this signal gets amplified to the bigness of that signal. All right, so, so this is a really nice result, so we can actually plot this function. So first of all, so we'll write this down here. So we'll think of it, this function's symmetric for about the y-axis there. So we really only need to look at the positive side. So we see that at omega naught, the function value is 1/2. Actually, yeah, it's 1/2. So it's actually 1 over root 2. Apologies for that. All right, so and we see that as omega goes to 0, we put that in there and we get all the way to 1. So for DC signals, so this right here would be DC signals, signals that don't oscillate at all. The amplification factor is 1. That means everything coming in here, it becomes the same amplitude out, so it's 1 to 1. But for values around omega naught, it goes down to this halfway point here, or close to halfway, 1 over root 2. And now, as we take omega going out bigger towards infinity, we see it decays away, like that. But how does it decay away here? Well, the amplitude, as omega gets larger and larger, is going to look a lot more like 1 over omega to the first power, as this term dominates and it becomes just, this becomes 1 over, effectively, the square root of omega over omega naught squared. So that's effectively 1 over omega like. Okay, and so I would actually, in terms of all the types of decay towards 0, this is fairly slow. At any rate, I would call this a fairly, not a very effective, but a somewhat low pass filter. And what we mean by that, and if you know anything about signal processing, small omega values, i.e. low frequencies, tend to be amplified to a greater degree. But very, very high frequencies are attenuated. So not much gets through if you have a very highly oscillating signal, a very quickly oscillating signal. Okay, so that pretty much wraps up this idea of the amplitude. But now what about, we're going to ask another question, which is, what about, so we know about amplitude, now I want to know about responsiveness. And what I mean is, if VI changes, so it goes like this, say, like that over some period of time, call that T star, let's say. And let's actually make this more concrete. Let's go to our real RC circuit. I'm going to actually turn on the signal like that, right at T star. Okay? So that is my T. I want to know what the V out looks like. Well, it turns out if you solve the differential equation, it'll look like this. It has a time scale tau c. Okay? And then eventually it'll reach 1. If the magnitude of my if that's 1 there, if the magnitude of my step is 1, it'll eventually reach 1 because, of course, DC signals all we already noticed that t at 0 is equal to, is equal to 1, right? So we expect the same amplitude to come out of it. But there is a slowness to respond, a slow to respond. So there seems to be some delay between when our signal turns on here at t star and when we finally approach, the rate at which we approach the asymptotic value. So how can we assess that? Well, we can do the same thing in the complex plane by, let's examine how V out is affected by V in through this. What this represents here is complex multiplication. Right, so we already know from complex multiplication that if I take z1 times z2, there are two actions that happen in the complex plane. One of them is if we have r1 e to the I theta and r2 e to the I theta, so that'll be theta 1, that'll be theta 2. We see that the magnitudes, the amplitudes then multiply r1, r2. And then we see also that there's this shift in the plane, this angular shift, theta 1 plus theta 2. Right, so in this particular, so what we're really interested then in, now if we can think of these signals, we can think of this as phase shifts. So for instance, if I have some signal V in is e to the I omega t, right? If I think of this as an input in the time domain, I'll call that omega c to distinguish it. I want to know what's going to happen in the output. The V output is going to look something like this. It's going to be the magnitude of our transfer function times e to the I. It's going to be some sort of phase shift that happens in the complex plane. So that'll be my phase shift. So that's simply representing the idea that although our amplitude jumps up to 1 here, for example, it takes a while for that to finally reach and to achieve, and so it might happen at a later time. And this phase shift then represents that delay. Okay, so let's talk about how to study that. So let's do that right here. So now let's, in order to do that, then we'll just go back to our equation. And we want to know then, if this is some complex number here, and this is some complex number here, we'll call that out, and that angle out, and that's in, I angle in, and this represents some other complex number. It's going to be, we'll call, it's going to be the magnitude of t e to the I phi. All right, in which case that becomes, and now if we take v out over v in, all with tildes, then we know that this has to be the magnitude of t e to the I phi. Of course, when we magnitude both of these things, this part goes away. But what we really want to study then is what this is. And we know we can get that from taking the principal argument of t. So let's go back to what t was. T was, again, it was 1 minus I omega. So now we're going to do this for I omega, and we plug that into it. I omega over omega naught, all over 1 plus omega over omega naught quantity squared. Okay, so let's let's see if we can figure out what this is. So of course what we have to do is remember what so if this is equal to x plus I y, we can see the real and imaginary parts, and we know that the argument is going to be equal to the inverse tangent of y over x. All right, so let's write down what that is. That's going to be inverse tangent, and we see our y value sitting there. It's going to be omega over omega naught. First of all, this term in the bottom, because it's multiplied by both the real and imaginary part, we can ignore it because it will divide out all over 1. But recall here there's a negative sign there, so let's put that negative sign there. But it turns out with inverse tangent, the negative sign goes right through because it's an odd function. All right, so let's write this out again. And so now let's plot this. We can see for right at omega naught, whatever it is, we're going to get inverse tangent of 1 times with a negative, and that turns out to be pi over 4. So it'll be negative pi over 4. Okay. Now if I take omega to 0, inverse tangent of 0 is 0, so we're up here at 0. Now if I take omega all the way to infinity, inverse tangent negative goes all the way to pi over 2, negative pi over 2. So we see our Bode plot, or our phase angle. So this is our phase. It looks like this. We have a point there. It kind of looks like this. So why the negative signs? That represents, again, a phase delay. In our signal. And ultimately, you can think of it as this way. If I have a V in that's some sort of sine omega t, V out is going to be some something like some sort of A cosine omega t plus phi plus B sine omega t plus phi. So phi represents that delay in our signal. Okay. So I should actually rewrite this. I made a mistake. That was a wrong statement. We can rewrite it as follows. The way we write it in follows is the magnitude of, there's some amplitude. And if this is a negative value, if negative, then what we get is a delay. So here we have some input like that, some sine wave, and we get is some diminished signal, but it's also delayed a little bit. So the amplitude's a little smaller, and it's shifted a little bit by phi. Okay, and so that shifting and amplitude decrement is captured by these two pieces of information, both the amplitude and the phase. So we can formalize this idea and actually call it a Bode plot. Is the combination of those two things. It is T I omega and phi. They usually write them like this, as follows. So we have omega down here, and we saw before that it started at 1, and at omega naught, like a little dotted line there, Our answer was as follows. We had a 1 over root 2 sitting there, and it decayed down. And we saw that it started at 0 degrees, it went down to negative 45 degrees, and then finally all the way to negative 90 degrees. So it did this. So this is called a Bode plot, and this gives you information about amplitude and phase. And so that's a really nice tool we can use to describe systems involving some sort of RLC circuit. So the next thing I want to do is go over one more example. And I know this is a long video, but it's worthwhile. So let's go over one more example now of a different type of circuit. Okay. So let's go over a different type of circuit to finish off here. All right. So the circuit I'm going to talk about it's very similar, but now I'm going to include an inductor. So here's my VI. There's my plus. There's my minus. And then I'm going to put an inductor, which you write as that coil. Put a capacitor there, and a resistor there. Now I'm going to measure the voltage V out across that capacitor, resistor, parallel capacitor and resistor. Okay, so it turns out, and again I'm not going to go over this in great detail, LC dV dt squared plus L over R dV dt, and this is V out, plus V out is equal to V in. Okay, so just like before, we take Laplace transform, and we assume that we don't have any initial conditions. We have 0 initial conditions for both the voltage and the derivative of the voltage. So we have LC S squared V tilde out plus LR times V tilde times S times V tilde out plus V out tilde equals V in tilde. Okay, so just like before, we can write this as follows. V out is equal to 1 over LC S squared plus L over R S plus 1 all over V in, V in. Okay, and of course this represents our transfer function of S. So it's a bit complicated, but we can do a little simplification here. We're going to let our omega naught, this is a special frequency, and this takes a little work to derive this to figure out that this is what it is, but we're going to say that it's actually equal to 1 over root LS, or sorry, LC. Okay, LC, in which case this transfer function becomes as follows. It becomes 1 over S over omega naught quantity squared plus what we'll call 1 over Q S over omega naught plus 1, where this Q factor here, Q is a different parameter now. We can find out what it is fairly straightforwardly. We know that that 1 over Q times omega naught is equal to L over R. So that means that 1 over Q has to be equal to L omega naught over R. So let's not worry too much about these parameters, but this is actually has a special name. It's called the quality factor. And we'll get to what that means in a second. But you can see it's a function of both. It's a function of both R, L, and C, and we'll see what it does for us in a little bit. At any rate, now we have our better representation of T of S. And then, of course, just like before, we take s to be equal to I omega. And now we're thinking about this as a result of a Fourier transform. And we're going to do the same analysis we've done before by looking at both the magnitude of t and also the phase of t. Okay, so we want to know what those two things are. All right, so let's find those. So again, we have t of I omega is equal to 1 over. And what we have here is we're going to put s in there. So s, I'm going to write this out in terms of s over omega plus 1 over q s over omega naught plus 1. Now I'm going to evaluate that at I omega, and that becomes 1 minus omega over omega naught, quantity squared. There's a 1 over all that, plus I omega over omega naught. I hope we see how we got that. When I plugged in the I omega there, when we square it, that becomes negative omega squared, and that's where that negative comes from. So we see here that's the real part, and then here's the imaginary part. Okay, so just like before, if I want to take, I want to simplify this, and it becomes 1 minus omega over omega naught, quantity squared, minus I omega over omega naught, okay, all over 1 minus omega over omega naught, all quantity squared, plus omega over omega naught, quantity squared. Oh, I forgot a quantity squared there. There we go. There's 2 quantity squares there. All right, and so we see here the magnitude of this thing, once we take the complex magnitude, and you can go through the arithmetic, it becomes 1 over, it becomes 1 over root 1 minus omega over omega naught, quantity squared, all that quantity squared, plus omega over omega naught, quantity squared. All right, so in terms of the Bode plot, the amplitude, we want to look at this. Oh, I forgot something. I forgot my q. There was a 1 over q there, so we need that 1 over q there as well, and a 1 over q there, and a 1 over q there. There's a q squared there, and a 1 over q squared. Okay. So now if I take the limit of omega going to 0 of the complex modulus of t, we see that has to equal, we can plug in the 0 value there, and that becomes square root of 1 minus 0, all quantity squared, plus 0, and that equals 1. Okay, so we have again, for DC current, for DC inputs, okay, so omega equals 0 as a DC input. We see we have an amplification factor of 1. And I want to know what happens for other values. Then, of course, we take limit omega going to infinity of t. And we see that this is going to have a slightly different behavior. It's certainly going to 0. But it's going to 0 at a different rate. It's for very large t, we see that this term here, there's a 4th order term there, and that becomes square rooted. So this is going to have a, I should write this as follows. I should say this has a 1 over omega squared type dependence for large omega values. Okay? And so it's going to decay a little faster towards 0 than our RLC circuit. So by adding this inductor, we've got a little bit different sort of behavior. So we're going to see that going off at 1 over omega squared down here. And then what about at omega naught? Well, if I put omega naught in here, it's clear that the limit as omega goes to omega naught, we're going to get a 1 over 0 root, that becomes a 1, so that becomes a 1 over q squared times 1, and that's equal to q. All right, so this is what we called a quality factor. So what's this quality factor do for us? So clearly q, if it's greater than 1, it's going to do something here. It's actually going to amplify our signal greater than 1, so it's going to do something like this before it starts decaying off. Or, so this is for q greater than 1, but if q is less than 1, you'll get something like this. But for the case here of q greater than 1, what we have here is what we call a bandpass filter. Where for a range of frequencies around omega naught, we get an amplification of the signal beyond what we get for DC inputs. So that's pretty neat. Okay, so now let's just quick-like study the complex argument here. So now let's study the phase shift. Okay, so Ken, this is equal to, it's going to be equal to the principal argument of t. All right, so let's write down what that is again. Remember that this is, oh, sorry, I must be dyslexic here. Arg, there we go. All right, and that's going to be in tangent inverse of the imaginary part of t over the real part of t. Okay, so remember t again was 1 minus omega over omega naught squared plus 1 over q squared omega over omega naught quantity squared all over 1 minus omega naught quantity squared minus I 1 over q omega over omega naught. And we can clearly see then that this result becomes negative inverse tangent of omega over omega naught 1 over q divided by 1 minus, we take the real part there, which is omega over omega naught quantity squared. All right, so this is a very, a little bit more interesting. So again, I'm going to go phi there. And now let's look at omega going to 0. So omega going to 0, we get clearly the phase is equal to 0, right? So again, we have up here, I'm going to put that 0 degrees, okay? And now for omega going to infinity, we're going to get slightly different thing going on here. We see that this is heading towards, it looks like this is, well, this is diverging, but this is diverging at a, so it looks like this thing is going to 0, but we see it's also doing something a little interesting because this term is dominating, but it's negative. So it turns out that phi is actually, it's actually going towards negative 90 degrees, or sorry, whoops, it's going to negative pi. All right, and that's because this is negative down there. And that's, of course, equal to negative 180 degrees. So we're going all the way down to negative 180 degrees down here for omega going really big, like that. But what about that omega naught case? We see there we have a division by 0. So tangent is going to be the tangent of this argument here of y over x, those being my imaginary and real parts respectively, is going to tangent infinity, and it's going to be heading towards negative 90 degrees. So it's right there, right in the middle, at negative 90. Okay, you can do this analysis. So it looks a little like this. What's interesting about this then, remember 180 degrees out of phase means that so here what we see here that any signal that's DC signal or really slow signal, right? If I'm right here, if a really slow signal, the system's able to track it pretty well with very little delay. So that's V in and that's V out, okay? But here we see that we have some signal going like that. It's going to be, so that's V in, V out is going to look like this. It's going to be slightly shifted as follows. Okay, when we get out here though, we actually get a complete inversion. It'll be a complete reversal out here, where here is our V in. It's going to look like this. Now, and V out is going to be completely opposite. It's going to be starting whenever we get to a low point in V in, it actually is as a high point for V out. You're approaching as omega gets bigger and bigger and bigger. It's as if it's almost going completely in the opposite direction. So that's for very high frequencies. And the other thing to note is that the amplitude of this is going to be very small relative to the amplitude here. So I haven't drawn it quite accurately. This actually needs to be like this. But that gives you the idea of what's going on here. So we see with these RLC circuits where we put in an inductor, we can get bandpass filters that let through admit certain frequencies at a higher amplification than a DC signal. All right, and so we've seen now some analysis using complex variables to do all this, and this gives us some really nice tools for characterizing linear RLC type circuits or any other circuit that we can find a transfer function for. Okay, so thank you very much.